Okay, I see. Okay, so today's topic is called Primal-dual algorithm. So it is in section 9.8. Okay. Basically, I have to say that when I reviewed the material yesterday night, I had no impression on this part. So what does this mean? It means that probably maybe it will not appear in homework or exam. So when you do your homework, if you don't see anything about this, so don't care too much about it. This is just for you can just treat it as learning it for fun. Okay. So for the primal-dual algorithm, basically the problem that it solves is still minimum cost flow problem. So remember last week we talked about successive shortest path algorithm, and now we're talking about primal-dual algorithm. Basically, they are both dealing with the minimum cost flow problem. So one thing that you may be curious about is what's the difference and what's in common for them. So let's say successive shortest path and primal-dual algorithm. That's just a briefly comparison. So for common thing and not common, excuse me, let me change another marker. So the common thing is that both of them maintains a pseudo flow. That satisfies reduced cost optimality condition. So remember that we said last week for the successive shortest path algorithm, it maintains a pseudo flow that satisfies the reduced cost optimality, which means that Cij pi is always greater than or equal to 0, and it gradually augment flow. So it gradually augment the flow so that the infeasibility reduce, and until the end, it is a feasible solution. And in this process, we always maintain the reduced cost optimality. So finally, we arrive at a feasible and optimal solution. This is the thing that is in common. And for and as for the things that are not common, for successive shortest path algorithm, we send flow along one shortest path. But for the primal-dual algorithm, we send flow along all shortest path. So this is what is not common between these two algorithms. So next we talk about how to do the primal-dual algorithm. So the first step, I think I can give you an example first. So suppose you have a very simple network, 3, 2, 4. Let's say, so we know that for the MCF problem, the balance of each node, we will assume them to be non-zero. So let's say node 1 has balance 2, node 2 has balance 2, and node 3 has balance -2, and node 4 has balance -2. And we have arc. Okay, we have arc like this. And on each arc, the first entry means the Cij, the cost of sending 1 unit of flow along this arc. And the second entry means the upper bound of flow on this arc. So we see the arc 1, 3 has unit cost 1, and the upper bound is 1. And let me write down the others. 1 and 2, 2. Okay, so this is the network. The first step first step is we add S and T. So this is a very common practice, right? So to artificially add a source node and a sink node, and we see that. So let's say we add S and T. Then what should we do? We add S and T. Then we need to make the balance of all the node 1, 2, 3, 4 to be 0. Then what should we do? What should we do? This was taught in network transformation section.
We add arc from the S to the supply nodes and make its capacity whatever supply those nodes have.
You mean in this way, right?
Yeah.
And also in this way. Right. So remember that the balance is outflow minus inflow should be, say for node 1, out minus in equals to 2. So that's to say, if we want to make it its balance to be 0, that's to say we need to add additional flow into this node. So that's the reason why we connect S1, and the same for S2 and 3T and 4T. Okay, and then that's to say, let's just call it the second step. We connect Si with, let's say, with Cij equals to 0, because we don't want to add additional cost on the arc, say S1, S2, 3T, 4T. So we just let them, excuse me, this is not Cij equals to 0, but Csi equals to 0, and USI, this is equal to BI if we have BI greater than 0. So that's to say, now, because we have already connected S1, so 1, 2's balance are both 0. And for S1, unit cost is 0, and the upper bound is, what's the upper bound? 2. Same for S2. And we also connect IT with CIT equals to 0 and UIT equals to minus BI if the BI is less than 0. So that's to say the balance of nodes 3 and 4 now becomes 0. And for 3T, unit cost is 0, upper bound is 2. And for 4T, unit cost is 0, upper bound is 2. Okay, that's it. And then now that we have node 1, 2, 3, 4 having balance 0, how about S and T? So let's say for S, finally we should arrive at, so in order to make node 1 and 2 have balance 2 each on each. So that's to say, these the arc S1 and arc S2 should be saturated finally, right? So that so what does this tell us? This tells us that the balance of S should be equal to 2 plus 2, which is 4. And for node T, finally we want 3T and 4T to be saturated, so that in this way the balance of 3 and 4 are both minus 2. So in this way, we need the balance of T finally to be also 4, to be minus 4, right? So we set BS equals to sigma I in N with BI greater than 0. We add them up. We want BS to be this, and BT, actually we can just write it as minus BS, the ease of writing. Okay, and also for all the intermediate nodes, we know that BI equals to 0 for any node I, which is not S or T. Okay, So in this way, we have transformed our network in this way. So S has balance 4, and T has balance -4. Then what can we conclude? So we can one observation that we have. We observe that the MCF in the transformed network is equivalent to MCF in the original network. Think about this observation. We observe that the MCF in the transform network in this way, is equivalent to the MCF in the original network. Is that obvious? How about you? Do you think it is obvious?
Yes.
Okay. So this is a very obvious observation. So this tells us that as long as we can solve the MCF problem in the transform network, it is equivalent. We can just erase ST and also the corresponding arcs, and this is the result for the original problem. Okay, this is a very easy observation. Then we define something. We need to so in order to carry out the Primal-dual algorithm, we need to define something called admissible network. Let's just call it G0X. So from this notation, you will see that it has some information about X, and as we said before, X means a network flow, right? So let's say X is a mapping from Rm to it's from the arc set to the real number, right? So X means the flow on each arc, and G0X it is defined in this way. Let's say we are given a network flow X and also node potential. Remember that we have been talking about node potential for several weeks, and node potential pi. We also need to suppose the Cij pi is greater than or equal to 0 for any ij. So that's to say the reduced cost optimality condition is satisfied. So we have given a network flow X, a node potential pi, and suppose Cij pi is greater than or equal to 0. And G0X, how do we obtain this admissible network? It is obtained by only keeping arcs in Gx with Cij pi equals to 0. So look at this definition. So G0X is obtained by only keeping the arcs in Gx with Cij pi equals to 0. So that's to say G0X is a subgraph from Gx, and Gx is the residual network. I'm pretty sure that you are very familiar with how to obtain a residual network given the original network and the flow X. Okay, so G0X is obtained by only keeping arcs in Gx with Cij pi equals to 0. My question is, can you imagine why do we need to define such admissible network G0x? Why do we only care about those arcs with reduced cost equal to 0? I want some intuition behind it. So in the textbook, the answer may just tell you, okay, you need to obtain this admissible network. But my question is there any intuition behind it? Thomas, do you have any idea? Okay, so this is, I'm talking about my understanding, okay? So remember that when we are talking about linear programming, the first algorithm that we introduced was simplex algorithm, right? So remember that in simplex algorithm, what are we doing? We have some polyhedron. And then every time we move from one vertex to another vertex, such that it increases it reduces the most to the objective function, right? That's to say you are going greedily in a greedy manner, right? So my understanding of the reason why we need to define such admissible network is that, so remember that all our operation is based on the fact that Cij pi is greater than or equal to 0. This is the reduced cost optimality condition. And based on this, we are keeping the optimality of the solution. We want to make the level of infeasibility to be smaller and smaller until the end, it becomes a feasible solution. And among all the arcs, we know that for every arc, Cij pi is greater than or equal to 0. And once there's something like Cij pi is less than 0, it violates the optimal condition, or optimal solution, the optimal reduced cost optimality condition. So which arcs among all the arcs in GX are the riskiest, are the most risky? Those with Cij pi equal to 0. So that's the reason why we want to take them out and deal with them. I think this is my understanding. Okay. Okay. So let me introduce the algorithm to you. So the algo called Primal-dual. So I will explain the reason why it is called Primal-dual later. And actually it is introduced in the last paragraph in section 9.8 in the textbook. So let's begin. So the algorithm for Primal-dual is like, we initialize the network flow to be 0 and pi equals to 0. This is the same as what we did in the successive shortest path algorithm, right? We just started with a trivial solution, a trivial flow, and a trivial node potential. And we define something called ES equals to BS and ET equals to BT. So this ES, how should we think about it? I think we can think about E as the excess. So ES equals to BS at first. And finally, we hope that we can reduce ES to 0. And in this way, the balance of node S become BS. And ET we initialize to be BT, which is minus 4 in the example that I had given. So we hope that during this process, ET will gradually increase until 0. So at the end, the balance of node T becomes just BT. Okay, so that's the condition for this while loop, while ES is positive. What should we do? We need to determine the shortest path distance. Let's say D from S to all other nodes in GX with respect to Cij. pi. So remember that at first I said in the Primal-dual algorithm, it is different from the thing that is different from successive shortest path is that in the successive shortest path, we also had a node S, but we just find the shortest path distance from S to some node. But now we need to determine the shortest path distance di from S to all other nodes in Gx. And the distance of each arc is just a Cij pi. How can we achieve this? How can we determine the shortest path distance from S to all other nodes? Extra?
Yeah, one of the.
Yeah.
And we have algorithms for it.
Yeah. So you can use Dijkstra, or if you want to be more secure, use Bellman for, right? Whatever. So single source shortest path distance. Okay. So as with you need to determine the shortest path distance from S to all other nodes in Gx with respect to Cij pi. So if you want to implement this algorithm, make sure that you can implement the Dijkstra algorithm at first, or say Bellman 4 at first. Okay, then we update pi equals to pi minus d. So remember that we have already said pi is the node potential, so it is in R node potential, what is the number of nodes? The number of nodes is n. So pi is in Rn, and d is also in Rn because it is the shortest path distance from S to all other nodes. So we can say that so it is a vector indeed. So we update pi equals to pi minus d. Oh, excuse me. I suddenly found an issue. I think x is not from A to R. X is a vector, not a function. So sorry about that. So I think x should just be Rm. Means the flow on each arc, because this is a vector, not a function. Sorry about that. Suddenly realized this issue. So we update pi, and then we define the miscible network G0x, and then we establish find max flow from S to T in G0x. So after we define the admissible network G0x, we find the max flow from S to T. We use the max flow algorithm to find the max flow from S to T in G0x. And suppose now we have already found the max flow from S to T in G0x. What should we do next? We update ES, ET, and GX. So that's to say, in each iteration of this while loop, finally we need to find the max flow from S to T in the admissible network. And suppose now, after we know that initially ES equals to 4 in the example that I've given, and suppose you found a max flow from S to T in G0x, which is like you give one unit of flow from S to 1 and 1 unit of flow from S to 2. So then ES equals to 4 minus 2 equals to 2. That's to say it has already sent out 2 units of flow. So from this perspective, you can say that ES is how much distance is the current balance of S to the objective balance, because the objective balance for S is 4. Currently, initially, because we have x equals to 0, so the current balance for S is just 0. ES measures the distance between where you are now and where's your objective. Is that clear? Okay. And then after you execute this while loop, finally you can make ES to be 0, and then you are done. right? Is there anything not clear?
Would ES equal to again?
Where?
Just so when we update ES, what do we update?
Like I just give you an example. Okay, so let's say you have S here. I just use the example that I had given, 3, 4, and T. So initially, you see that remember ES equals to BS. So that's to say initially we have ES equals to 4, right? As I said, ES measures how much distance you are between where you are now and where's your objective. Because to make this problem to be feasible, to make this solution to be feasible, we want S to send 2 units of flow to 1 and 2 units of flow to 2. Because S1, S2 should be saturated, right? And 3T and 4T, they should be saturated. So that's to say there should be 2 units of flow from 3 to T, 2 units of flow from 4 to T. So we see that ES, initially it is 4. And finally, we want ES to be 0. So that's to say, we can understand ES in this way. We can say that ES measures how much you are from the current balance to the objective balance. For S, your objective balance is 4. Initially, because you have 0 flow. Because you have 0 flow, so the initial balance is 0. And after, say, let's say in this step, you find the max flow from S to T in T0x. Let's say you send 1 unit flow through S21 and 1 unit of flow through S22. Then that's to say your current balance is 2, right? Because you have already sent 1 unit flow to 1, 1 unit flow to 2. So now, what's your ES? Your ES is just 2.
Oh, cool. Yeah, that makes sense.
Yeah, okay, makes sense. Very nice. So as for the reason why it is called Primal-dual, I will just read it out. So the name Primal-dual stems from linear programming duality theory. So in the linear programming literature, the Primal-dual algorithm always maintains a dual feasible solution pi, and a primal solution that might violate some constraints. So that's the that's to say, in solving this kind of MCF problem, we have the node potential pi, and we know that we always make Cij pi greater than or equal to 0 to maintain the optimality condition. However, we know that initially it is not a feasible solution. So that's to say, that in the primal problem, it is infeasible. And for a given dual feasible solution, the algorithm attempts to decrease the degree of primal infeasibility to the minimum possible level. So that's what I explained at first. I said that you start from an infeasible solution and you gradually decrease the level of infeasibility until the end you will get a feasible solution. Yeah, so that's the idea behind it. Right. So as I said, we don't have that much content today, so that's all for today. Very nice, right? And earlier.